Good day, everyone. My name is Gordon Lacy. I am lead engineer on the NGVLA telescope development project here at DRIO NRC. And today I'm going to be talking about developing the NGVLA 6-meter radio telescope. A bit of an overview. First I'll talk about what is the NGVLA project, the evolution of composite reflectors at DRIO, close packing requirements, the evolution of the 6-meter design, the current design concept, analysis results, development of the mount, and next steps, and finally the summary. Starting with what is the NGVLA project? Well, NG stands for next generation, and it's a large array planned as an upgrade or replacement for the 27-dish VLA array. The new array will consist of 214 18-meter radio reflectors with a short baseline array of 19 6-meter reflectors at the core and a long baseline array of 30 18-meter antennas which will span across North America. Frequency range is 1.2 gigahertz up to 116 gigahertz. Progression from the earlier DVA design. So DVA stands for Ditch Verification Antenna. It's now 2 antennas that we've built at DRIO to prove the concept of rim-supported single-piece carbon composite reflectors. The NGVLA 6-meter and 18-meter designs that we've developed are a logical progression from these 2 designs, the DVA designs. They share some similarities, quite a few actually. They're both single-skin carbon, single-piece carbon reflectors. They're rim-supported. They're supported at discrete points with a tubular back structure. In the case of DVA, it's steel. The layup of the primary and secondary, the layups are the same, and the reflective technologies that we developed is the same. Just to start the development of the 6-meter, we scaled down the 18-meter design that we had done, which is now the reference design for the NGVLA project. This 6-meter design can be seen on the right, and it's a straight scale down. Some things changed, like the hub is now, or was then, steel plate instead of tubular structure, but this is just a scale effect. However, this design didn't meet the requirements exactly, at least the one requirement, which was minimum close packing distance of 11 meters, and with the first scale down design we could only make 14.8 meters, which with the telescopes pointing in opposite directions, which is a requirement. So we had to redevelop the back structure, the bus, the backup structure, and here's a few of the many steps that we went through. We had to pull the elevation axis up to underneath the rim of the primary, move it towards the base, offset it from the geometric center, as well as center it over the elevation or azimuth axis. And this is a little visual showing the steps involved. The bottom right one is the bus is now a carbon tub. This was necessitated by the weight of steel and the difficulty in getting it to balance. With these changes, we're able to meet and exceed the 11-meter close packing requirement. In fact, we can make 9.6 meters, as you can see in this graphic. Now, the NGVLA design, what do we have? This picture on the right shows the current design. It still is a single-piece primary and secondary reflector, carbon composite reflector, edge supported. You can see the red tubes are the edge support tubes. The bus or backup structure consists of those red support tubes plus a carbon fiber tub, which is made up of cord composite panels, and that's the gray portion. secondary support structure, and the secondary is all carbon. You can see it here. And then the mount is a combination of steel plate and steel tubes. Feed indexer is meant to be the same as on the 18 meter, so we have to accommodate what would be a rather large indexer for a 6 meter, has to be fit as well. The drive system is either a linear drive or a gear drive. A little bit of detail now. The rim design on the primary, now with this design is a curved rim. The green portion represents the dish surface with the rim. And then the brown portion is what we call the composite backing pieces. This is bonded in, and it is spreads the load out from the discrete black struts in this picture. We have the ability to isolate the hard point from the support a little bit with the composite backing piece, separate it from the surface of the dish, and pull a lot of the structure outside of the optical surface, which would start at the top inner edge of that radius. We can also tune the bottom of these pockets in the composite backing piece for stiffness, thereby softening the hard point to some extent, which is a homology-like effect. We also have the shear connection, or what I call the shear connection. It's between the dish surface, which is the yellow portion in the left-hand image, semi-transparent, and the gray, which is the bus. We have the red tubes. That's the outer back structure, I call it. But there's no diagonal support, so that the yellow surface will fall vertically in that picture if it wasn't supported with some kind of a diagonal tube. Diagonal tubes also constrain the structure unnecessarily in, under a CT or under a thermal expansion. We don't want that. So we have a single point, which we call the shear connection, here shown as a double blade. And it's a blade because it has a double hinge, so that movement in and out of the page in the Y direction, coordinates are on the lower left, is allowed. It's stiff in X, which is in the plane of the dish surface, the long axis of the reflector, and there is some softness in Z, both accommodated by the two arms sticking out from the elevation axis and the softness of the let me just get the pointer here. The softness of this surface in the composite backing piece that can be tuned to allow a little bit. The backup structure or bus is like I said earlier, is a carbon fiber tub. It's made of carbon fiber and foam core panels. It's constructed somewhat like a boat. It has a lot of bulkheads in it to stiffen it. And the detailed pieces on the top, which can carry the point loads, would be made out of steel. That's the elevation axis support, and the 2 points here, which are the supports for the secondary substructure. Secondary is also supported here at the elevation axis. This structure is made out of steel, but the CT, the coefficient of thermal expansion, is quite closely matched between steel, which is 12 parts per million per degree C, and carbon with a foam core, which is around 10. We've done quite a bit of topology optimization with this telescope, and this is just one example. The side structure that holds up the secondary topology optimizing program comes up with some crazy design like this, but it does help show what the load paths are and where the best place to put materials. We can't build these parts directly unless we were going to 3D print them or cast them. So we have to use this interpretively to develop our own structure, but that's what we've done. Base support for the secondary is taken on 4 points. 3 are shown by arrows here. As mentioned earlier, what I call the forward feed leg lands on the elevation support, and then the other 2 directly underneath the secondary are supported by these tube tripods off of the bus. This is different from the DDA design in that these loads are somewhat isolated from the surface, On the DVA, these struts land directly on the rim. Now moving on to some results. These are plots showing the RMS best fit error looking in the focal plane. The actual dish is somewhat elliptical. You can see that we have, at 90 degrees elevation angle, we have 39 microns of error from gravitational distortion. And at 53 degrees, halfway through the elevation range, we have 21 microns. And this model includes all of the back structure and the mount. A summary table showing more results. The integrated model, we have a natural frequency of 3.67 hertz. We have 38 microns at elevation angle of 90 degrees, 21 at 53, and 42 at 15. We can tune the structure, which is we've only just started to do, mimicking a rigging angle adjustment in the field in the FEA program by putting in some preloads. And we've begun to do that, and you can see the potential of it here in the lower right table, but we haven't completed the operation, only having modified a couple of struts. Thermal analysis, we went through with steel tubes replacing the red, or for the red tubes shown in the earlier picture. But to get the error down to the lowest possible, we had to replace some of those tubes with carbon fiber in an attempt to match CT matching. And this brought the error down to 33 microns. Secondary dish surface distortion, we've done the dish with its quasi kinematic mount. Quasi because there's 4 instead of 3 mounts. 2 of them are pin instead of 1. And this removes 1 degree of freedom. Out of plane twisting of the reflector is not isolated, but we don't expect that to be much of a problem. And the support is much better with 4 versus 3. We have got 11 microns error, roughly 11.5 in both elevation or any elevation angle. This is not a complete structure. This is just a secondary mounted on its mounts. We still have to include finish the analysis on the rest of the support structure. A quick mount overview. Nathan Lowen of Sightline Engineering has done the mount design. It's steel because steel is the best material for this. Weight is not really a consideration. It's a plate and tube structure. The gray part, of course, is the plate structure, which is now evolved into a nice base for mounting various pieces of equipment, which is required. And then the upper part, the yoke part, is made up of steel tubes and another little stand which holds the drive motor system. The elevation drive, this is a toe link concept, so the idea is to isolate the gear loads from producing radial loads into the back structure. We don't really want to do that because it is quite a big structure, and it's being a large yoke, there would be a fair amount of spring in it. So with the second motor for backlash control, to jam the 2 gears together, it would create some radial loads. These are now taken with this floating toe link concept. The 2 motors are on a floating carriage, and it's guided by a rail with 2 wheels on it or more. The benefits are many, including this removing the radial component of the load, but also it relaxes the global runout tolerances of the rack, which is a rather nice thing. Next steps. Further iteration on secondary feed and support structure to improve stiffness is something that we have to do. We need to finish the detailed design of the feed indexer and feed indexer support interface. We need to do the detailed design of the primary backup structure. We haven't completed any of the joint designs. Full wind eigenvalue and thermal gradient analysis needs to be completed. I don't expect any problem with the wind analysis. Room-supported designs seem to be very wind agnostic. And composite material characterization, we're doing this in the lab, including coefficient of thermal expansion, coefficient of moisture expansion, process-induced distortion, and hail impact tests. In summary, telescope design now meets gravitational and thermal requirements. Other than the gradient, we haven't finished doing that analysis. Wind analysis still needs to be done, but like I said, it's unlikely this will lead to any significant changes. And I'm confident we can meet or exceed all of the required NGVLA 6-meter specifications. Thank you.